Hello, hi everyone. I'm sorry, I was ill for the last couple of weeks, actually several weeks. I had some flu, I believe, but this year's flu was really bad. So I'm still not 100%. I believe we missed 2 weeks. Fortunately, we do have videos from last year. Um, Essentially the same content. So I don't remember whether I posted the video for the last week, which was week 13. I did uh, post the video for week 12, I believe. So unfortunately, from week to week, we do not have too much dependency. So it's not something that you have to follow every week. So I will make sure that for the last 2 weeks, I will post the videos from last year. So when you have time, it's up to you whether you want to watch those videos and check your work. Sorry, I'm still coughing quite a bit. Um, so for today, for this week, we are in week 14, which is geometry. So this week's geometry is something I believe we did not discuss before. So it's mostly about kinds of problems. Someone like the folks at the AOPS art of problem solving, they call this funky area problems. So this is one of the just favorite problems that the Mathcounts or AMC8 just organizers like to put into the exam. So essentially, you have some quite interesting geometry problem where you have certain geometric figures mixed together, could be a square, circle, semicircle, or rectangle, and so on. They tend to kind of combine, so they intersect with each other, and some intersected areas or area, they are marked as shadowed areas, and you are asked to compute such shadowed area with the given parameters of the geometric figures. So those problems could be fairly easy, like this one, or could be sometimes, depending on what figures provided, it could be fairly challenging. But the underlying principle for solving those type problem, whether easy or challenging, the principles are essentially the same. So basically, all you need is to make a very careful observations about the shadowed area to see all the curves, the size that made up the area, and to see what is the connection for those line segment or curves. What is the relationship with any particular one with the rest of the figure? And from such relationship, how can you derive some essentially combination of areas? By combination, you need to perform subtraction and addition. So it's really the final result could be something like this. So like A plus B minus C plus D minus E minus F. I'm just trying to make it up. So all that means that A could be a certain area that you can relatively easy to compute, and so is B, C, or D, E, F. Each individual ones could be relatively straightforward. but they can be mixed together in such a combination that results in the shadowed area that you are asked to compute. It's this kind of combination that it's hard to directly identify. It could be relatively simple, but it could be quite complicated, like this one. So this one is fairly complicated. Okay, so your job is to identify such an overall relationship, but you don't have to get it done all at once. You can identify each individual one at a time. So this is quite at a high level, in the abstract. So you may want to take a particular look at a specific problem to understand what we are talking about. So for this problem, we have a square in the outside. We know the side length is A units. So we have one arc that is centered at A. That is the other one is C. So what that means is that we have two, not just one, two just arcs that are part of two circles. So for example, for this one, dB along this curve. So dB is part of the circle that has a center at A, and one of the side, either AD or AB, as the radius. So if you draw that circle, you will get a circle, but we are only getting 1/4 of that circle. Similarly, if you choose C as the center, you get another circle, but also just 1/4 of that circle. So you get the other arc dB, which is this lower one. The two combine together to give this shaded area, this shadowed area. So how can we compute this particular shadowed area? So if you have never done any problem like this, you may, at the beginning, you may feel, I don't know where to start. But one important idea for solving those problems is that if the figure looks a little bit complicated, then you want to focus on one part of that figure at a time. So what's exactly made of this figure? We have two curves, right? So each curve has a very special and pre-specified property. That is that it's part of a circle. So let's just focus one at a time. By that, we mean something like this. This is the square, and this is one of the arc, and two arcs. What if we temporarily forget about one of them? So let's just, for now, consider one arc. Now, do you see what is the relationship between this blue arc and the rest of figure? Clearly, this arc gives us 1/4 of the circle, right? So it does divide this square into two parts, and we will be able to get the area of this quarter circle, right? Because we know the radius, which is 8. So we know pi r squared equals to pi times a squared. And then you get 1/4 of it because this is 90 degrees. So essentially you have a circle, but you only get 1/4 of it. So we know the shadowed, for now, the shadowed area is this one divided by 4. So we know this. Once we know the area of this quarter circle, then we can get the area of the rest of the square. That is simply the total area subtracting the quarter circle area, which is a sector. So we know the total area of the square is 64. So if we put this part as A and this part as B, then clearly area B is 64 minus this number, which is 16 pi, right? Because a squared is 64 divided by 4, that's 16, so that's 16 pi. At the same time, this is a B. At the same time, we know A is just 16 pi. So that is what we get if we just focus on one curve. Now, if we do have the second curve, what happened? Well, because in this particular figure, it's quite straightforward because the two are kind of symmetrical. So by the same argument, now we have three different areas. If we call this A, which is what we want, then we have another area C. So by this symmetry, we can see that area C is essentially the same as B, right? Because area C now is just this portion of the square. So C must be also 64 minus 16 pi. That gives us the direction of finding area A. Now, you can see that because both B and C are known, A is again the total, the new A. Let's call this A1. Now, that was before we change the figure. Now, just to avoid a little bit confusion, let's call this A2. So A2 is what we want. Now it's 64, which is the total, subtracting B and C. Okay, so that is 64 subtracting 2 times 64 minus 16 pi. So from here, you can see that by a little bit manipulation, you can see that this would be 32 pi. 64 minus 2 times 64 minus 64. So the area that we really want is this number. But how did we get there? Essentially, we are just trying to see if we see this C and this B can be both considered as a total area. If we say the total area, let's use different set of just letters for that. If we say the total area is Z, and the quarter of the circle, that's what we derived earlier, call that Y. Then we are doing a total Z subtracting 2 times Z minus Y. Just to avoid confusing, Z represents the total area of the square. That's the area of square, where Y is the area of the quarter of the circle. And Z minus Y represent either B or C. So that is what you need to do. Okay, clearly that would be 2Y minus Z. Okay, but this also gives us another idea or other interpretation of what is going on. So if you think about it, this shadowed area can also be considered if we first have a quarter circle or a sector, a 90-degree sector like this, then we put a second copy onto it. If we have two such quarters circle or sectors, when we combine them together, one on top of the other, the two will have some overlap, right? And that overlap is exactly this shadowed area that we want to get. But this is a little bit more difficult to observe the first time around. So essentially what we are doing is that we are combining two sectors. They produce an overlapped area. But if we subtract the square from this combo, that will give us the overlapped area. In other words, those two sectors, when we combine them, they generally give us a square plus the overlapped area, because that overlapped area will appear twice, one inside the square, one on top of that square. So that really tells us this shadowed area is just 2y, which means the two sectors, the area, then subtracting the whole square. So both will give us the same result. It's just that we interpret this result in two different ways. So in this way, we first calculate this area and then this area, which is through this z minus y. Then we subtracting those two from the total. That's one way to look at this shadowed area. The other way is that we think this is the kind of surplus when we combine two sectors, which generate a square plus some surplus. So we add those two sectors, subtracting the resulting square, then the remaining one is the area of this sector. Of course, the two are exactly the same. In fact, we see this from this in the first place. But this problem is very simple, but it gives us a lot of kind of insights into how to attack this type of problem. That is, all those funky areas, no matter how complicated, it's the result of certain combination of areas that are relatively or sometimes very straightforward to compute, whose areas are very easy to compute. Okay, so this is one that it doesn't take too long to see how to combine them, but some will be more challenging, as we will see later today. Okay, but it's very important to get the insight into this type of problem. And one takeaway is that if the figure looks complicated, try not to do everything all at once. Try to take one part of the figure at a time. So if you just say, in this case, we have two curves. If you just take one curve and then figure out what exactly does this curve do? Well, like we saw earlier, this curve gives us a sector and the rest of the square. Okay? All right, that's the first problem. It's a very simple problem, but if you never work on this type of problem before, it's a good starting point. Okay, this one is a little bit just a kind of just unique in this week's problem. I believe this problem appeared quite several times throughout the Mathcounts mini series. I I don't remember exactly whether we discussed this before, but this is a very challenging problem, in part because the very figure that was provided by Mathcount is very misleading. So this is a 3D geometry problem. It's not to be this difficult if we do not have this figure at all. So the figure does not really help, but actually can confuse you. So let's read this problem a little bit more carefully. So we have faced ABC and DF of the polyhedron below that are parallel equilateral triangles. So ABC and DF are both equilateral triangles, and they are parallel to each other. So because this is a 3D geometry problem, you have to try very hard to have some spatial imagination about the geometrical figure here. So ABC and DF, it's not very easy to see here, but they are parallel each other. And from the figure, well, the figure is misleading, but at least it's not randomly drawn. So at least it should be reasonably close to the problem. So D looks like it just toward us, while A is away from us. Okay, and we know the side lengths of both equilateral triangles. That is 4 times square root 2. But the next statement says that each of the outer edges in the polyhedron have length 4 unit. So, and it's in particular AE. Well, AE is hard to see because look, AE in this figure is a dotted line, meaning that we cannot immediately see this edge. It's on the other side of this 3D figure. And AF and EC we can see. EC looks like a vertical one, and BF that looks another vertical one. Then we have CD, which is observable, and DB. They are all 4. So this provides some really challenging because this figure was not drawn according to the scale. Clearly, there's no way if BC here, is 4 square root of 2. There's no way CE and the BF is just 4. So that made this problem kind of just, the figure was drawn in such a out of proportion way, it just severely distort our imagination of what the figure should be, right? Because CE and the BF looks like vertical, and they should be what they are. The only way for this to happen is that this triangle ABC and DF are so off that they are not kind of over each other, but in the very they shifted away from each other so much that the BF and CE are not actually vertical at all. So only in that way the figure can look like this. But if that's the case, there's no way actually for BD and the CD to be 4. So how can you visualize this figure? Well, before doing that, one thing you should be very sensitive to is that look at the numbers. We have 4 square root 2 and a lot of 4. So that means that the ratio is 1 to square root of 2, right? Especially we know CD and the BD are both 4. So that is the isosceles triangle. At the same time, BC is 4 square root of 2. That tells us that what? We have a triangle. We have a triangle that is 4, 4, 4 square root of 2. And what is that triangle? That's a 45, 45 right triangle. So this is a right triangle and this is 45. So that means that in this case, we have a right triangle, which is a, it's pretty clear that D is not, this plane BCD is not a vertical one. It looks like it's just BD, D is toward us, but BC is away from us. Okay, so now we know this is a 45, 45, 90 a triangle. But how about the other triangles? Like a CDE, what is that? Well, we don't know. DE is also 4 square root of 2, right? Because DEF is a equilateral triangle. So this is also 4 square root of 2. But DC is 4 and CE is 4 as well. So this is actually also a 45, 45 right triangle. And the right triangle is the angle facing the longer side, which is DE. So that means that the angle DCE is a right angle. But this clearly doesn't appear to be that way. That's why this figure is so misleading. But from here, you really cannot just imagine what kind of figure is that. Oh, by the way, by symmetry, BDF is also such a 45, 45, 90 triangle. So we really cannot imagine what kind of figure we are having. Because this figure, the way it was drawn, doesn't make sense at all. So that's why this problem is so difficult. If you don't have this figure at all, then it's very hard to even draw this figure in the first place. As it turned out, I don't think this is a good problem because 3D, this kind of 3D geometry problem is already challenging all by itself. You have to have very solid, just a spatial imagination to visualize the figure. But on top of that, the figure was drawn in such a misleading way, it makes it tremendously difficult. So as it turned out, the actual figure should be something like this. You have a cube, okay? Then you cut off 2 big corners. The corners is not a tiny corner, but a huge corner. Actually, it takes a pyramid off. So in this case, what we have on the leftmost figure, which is shown in the problem, is the result if we cut off 2 pyramid corner in a symmetrical way from this cube. And assuming the side of the side length of this cube is 4, obviously just the surface square diagonal would be 4 square root of 2. And that is exactly what happened in this figure. So if you imagine for this particular one, if we cut off the red line shaped 2 corners, one is XABC from this corner, and we cut off another remote parallelly from the other remote corner Z, so we cut off ZDF. That is another big corner, which is a pyramid. Then what we will have for the remaining part of this cube is just this. If you compare carefully, everything will make sense, because now clearly you see that ABC is actually parallel to DEF just by the symmetry. Okay, it can actually be proven, but you can feel you don't need have really just some 3D geometry knowledge. You can see that ABC is actually parallel to DEF because they're symmetrically carved, and that meets our first condition that ABC and DEF are parallel equilateral triangle. And it's clearly here ABC is an equilateral triangle because each side is a diagonal of one of the three surfaces. Those three surfaces form the big corner that was cut off. So you just compare those two, you can clearly see after we cut off those two big corners, the remaining part of the cube is exactly the figure given here. So I don't think this is a very good problem at all. It's kind of at least unfair, but it is what it is. So now the question is that how do we calculate the volume of this figure? Well, if we can clearly equate this to this, then the answer is quite simple, right? We start with a cube, which we know how to compute the volume, because the side length is 4, so the total volume is just 4 cubed, that is 64. Then we cut off two big corners, okay? So they're the same, so we just need to compute one at a time. And you have to know how to compute the volume of such a figure. Well, if you think about ABC is the base, then it's very hard. Although we know ABC is an equilateral triangle with a side length 4 square root 2, we can compute the area of such an equilateral triangle. But in this case, it will be very difficult to compute the height, because the height would be from the other vertex, which is x, you draw perpendicular to the triangle ABC. So if you look at this figure that way, it will be very difficult. But this cannot be that difficult because this is a part of the corner of a cube. So you have to just look at this from a different angle. That is, if you take any of those three other faces as the base, all the other three faces are 45, 45, 90 degree triangle. So for example, if you take BXC, which is the 45, 45 right triangle as the base, then what is the height of this? Then the height would be XA, which is perpendicular to triangle XBC. In other words, you just rotate this a little bit, choose an easy to compute surface as the base, then the height of this just a pyramid will be very easy to get, which is just side length. So clearly, if you take that way, the base would be 4 times 4 divided by 2. That's the area of that 45, 45 triangle. Then the height will be also 4. Then you know for the pyramid, when you do the volume, you have the base times the height, but you have to times that by 1/3. Make sure that you know the general formula for how to compute any pyramid or a cone. It's just like the area of the base times the height, then times 1/3. So this would be the volume of the corner that was cut off, because we cut off 2 such corners. So you just multiply that by 2. That's the total volume that you cut. So then we subtract that from the total volume, which is 4 cubed. Then this gives us the volume in question. This is what we want. Okay? So this problem is very challenging because you cannot easily visualize what happened. What is exactly this animal? What is it? It's what we cut off 2 big corners from the cube. But apparently, the figure will not give you that understanding at all. So that's why it's so challenging. All right. I hope in the future Mathcounts will not have a problem like this. It's quite unfair. Okay, it is what it is. So now, problem 3. So now we have a true funky area problem. Oh, by the way, you can consider this problem as a funky volume problem, right? It just conceptually similar to funky area. I guess that's why it appears in the same meaning. It's just from area to volume, but essentially it's still the same thing. You combine certain geometric figures to get the quantity. Okay, let's take a look at this problem. So here we have a triangle ABC, which is equilateral, which is nice. We only have one parameter, that is side length. Then we have arc centered C that is tangent to the other side facing this vertex. So what is the total area of the shaded region? This is very straightforward, right? Clearly, the shaded regions, in this case because it's tangent, so effectively we have 2 while they are connected at that tangent point, but technically it looks like 2 small regions. But if you consider that as a whole, if you consider that single point can connect to, that's fine too. So what is that? It's apparently the total area subtracting the sector area. So what we mean is we have equilateral triangle. It's not perfect, but hopefully. So then you take one vertex as the center, you draw an arc, which means that it's part of a circle, and this happens to be tangent to the other one. But because this is such a nice figure, we clearly know if we connect this center to this tangent point, this will be perpendicular to this side because it's tangent. So those 2 small shaded areas, regions area must be the total triangle subtracting this sector area. And that is very easy to compute because it's the equilateral triangle, so we know this angle is 60 degrees. That means that this sector is just 1/6 of the circle, underlying circle, right? So it's essentially a circle, but we just take 1/6 of it. The only problem is that, do we know the radius? Well, it's not directly given, but because we know the side length, this is 1/2 of equilateral triangle is 30, 60, 90 triangle. So this can be clearly, easily computed. So if the side length of this equilateral triangle is AB, so the side length is 6, right? So what is the radius? Radius must be 6 times because this is this longer side of the 30, 60, 90 triangle. This must be square root of 3 over 2. Always remember a 30, 60, 90 triangle, the 3 sides is this is 1, This is 2, and this is square root of 3. The hypotenuse is 2, the shorter side is 1, and the longer side is square root of 3. And clearly understand the three sides relationship so that when you use proportion to get one from the other, you will not use the wrong proportion. Okay, so if this is 6, then this must be 6 times square root of 3 over 2, and this is 3 times 3 square root of 3. That is radius of the underlying circle. So the sector's area must be pi r squared divided by 6. That is pi times this square, which is 27, divided by 6. Okay, so this is the area of the sector. Now, what is the area of the total this equilateral triangle? Don't forget the formula for that. When we have an equilateral triangle, this is also very fundamental. You do need to memorize a certain things, right? If you have an equilateral triangle that has side length of A, what is the area of the equilateral triangle? It's square root of 3 over 4 times A squared. Okay, of course, this can be easily proven, but you don't want to calculate this on the fly. You need to memorize it. Come on, you have to memorize some basic stuff. It's your choice whether you want to memorize it or spend time during a very kind of time constrained exam to derive this number on the spot. You don't want to do that. So this is total area is this number times side, which is 6 times square. So the shaded area is just this. Okay, so clearly 6 squared, that's 36. So this is 9 times square root of 3. Subtracting, we can cancel out the 3, subtracting this number. Okay, you can factor out the 9 or you don't have to. But regardless, this is the area of the shaded area. This problem is very straightforward too, because it's very clear how you can compute the shaded area. The rest is just testing you some basic geometric knowledge. So you just need to know this is sector and how to do a sector, how to do the area of the equilateral triangle, and so on. But nothing difficult at all. Okay, so all right, this problem is a little bit more challenging, but make sure that you understand what we are trying to do. Okay, we have a weird shaded shape. How it was constructed? Well, we have a big semicircle, right? So the big semicircle here, semicircle's diameters, and CD is, which is the diameter of the big circle, is square root of 2. So we first have a big semicircle that has the diameter as square root of 2. Okay, now we have a smaller semicircle that has diameter 1. You just like imagine somehow you move this semicircle, move until this diameter AB becomes a chord of this big circle. Okay, so you can imagine you start somewhere from here, which is smaller, diameter 1 semicircle. You just, of course, the two centers align. You move until this one intersect the semicircle just that way. So now you have this kind of overlapping. So the shaded area is really this part. By this understanding how this is actually constructed, then you will get some idea. But let's stay with the principles we stated earlier. So we want to know the area of this weird shape. What is made of? It's made of two arcs. This arc, which is quite straightforward. This is a semicircle, right? And this arc, well, what is this one? This is a portion of the big semicircle, but with two endpoints that is so deterministically given because this is a chord which happens to be the diameter of the smaller semicircle. So let's focus on one at a time. If we temporarily ignore this second curve or arc, only look at the first one, what do we have? This is just semicircle. We know how to do it very clearly. It's just 1/2 of the circle, half of pi r squared. So we know how to do this because the diameter is given. So the radius here is just 1/2 because diameter 2. We know this part. Then on top of this, we added the second arc, which is this one. That cut off a portion from the semicircle. So the targeted shaded area is clearly just the area of the smaller semicircle subtracting this area. Okay, so our problem got a little bit simplified. Originally, we need to compute a fairly challenging shaded area, which is made of two arcs. Now, we reduce that problem to a simpler problem, that is compute the shaded area, the green shaded area. We still don't know this immediately, but this looks simpler because this one has a straight line and only one arc. If we can compute this one, then we can compute the red shaded, the original shaded area by subtracting the green one from the smaller semicircle. But how can we compute this one? Well, at least this is simpler than the original problem, right? Now we have just one arc, but one straight line segment. You have to think about what are they. So this arc is determined by this line segment, which is a chord. And we do know its length. But how do we relate this to the rest of the figure, which is this big semicircle? So at this point, you might want to remove from your mind about that part because we already know that's what we want to do. If I just give you this figure, can you really figure out the green shaded area? That is completely decided by what those 2 points are, right? Those 2 points give us an arc that is with a side 1. And we know the big semicircle's radius square root of 2. But what this do? It gives you 2 points on the semicircle. So you will naturally think this can be, those 2 points should be connected to the center of the semicircle. Now you see what happened. The green shaded area is just the difference between this sector and this triangle, right? Do we know the angle? And do we know what kind of triangle is this? Well, usually in the math count or AMC roof type problem, the numbers will be fairly kind of helpful for you to figure. If this rate of the diameter is square root of 2, then the radius will be square root of 2 over 2, right? It's just 1/2 of the diameter. That will be the radius. But what is this? This line segment is the diameter of the smaller semicircle, which is 1. So we have a triangle. This is 1. This is square root of 2 over 2. And this is the isosceles triangle. You should be fairly good at numbers. You will immediately see the ratio between the longer side with smaller side is just square root of 2. What that means is that this is actually a 45 right triangle, right? You have to remember such a relationship. When you have a 45 right triangle, the three sides are 1, 1, square root of 2. So this triangle is just, we proportionally shrink every side by a factor. That factor is this. We times this to all the three sides, then we get exact this. So this is indeed a 45 right triangle. Bingo! We know how to do this. And that also tells you this angle is 90 degrees. Therefore, this sector is just a quarter of the circle and just 1/2 of the semicircle. But regardless, we know how to do this. So this problem becomes immediately clear how to do it, right? In order to get the original shaded area, we just want to compute this green shaded area, because from there we can do subtraction from the semicircle. But to get it from here, clearly we just need to further subtracting this triangle from this sector. Okay, so now if we just do this in English, the green one equals to the semicircle subtracting, oh no, I'm sorry, the red one is our target. It's just semicircle subtracting the green, right? And what is the green? The green is the sector subtracting the triangle. So if you put this into this, then you can see the red just equals to the small semicircle add the triangle, because now you're subtracting the green, negative becomes positive, and subtracting the sector. Now you can see that if you think that way, this is truly just adding this sector, then this semicircle, so the semicircle plus the triangle, then subtracting this sector. Okay, so you can think about it. If you add this semicircle with this triangle, you got like an ice cream cone, right? So you get something like this. This is like an ice cream cone. Then subtracting this sector. That's what you got. But this relationship is not obvious at the very beginning. You may not immediately recognize this, which is okay, because you are not supposed to get a direct result in one shot. But by analysis, we will see how step by step we still can derive this relationship. We just focus on what we have. If you first focus on the outer arc, that's the semicircle, and the semicircle subtracting this green one is the most obvious observation. That gives us a target. But the green one can be further presented as this sector subtracting the triangle. Once you see that, the final combination is really the semicircle plus this triangle that's subtracting the green sector. It's not that difficult. It's just that it takes multiple steps. If you really observe this final relationship upon the first look, congratulations, you really have very outstanding feeling about the geometric figures. But most people don't. If I try this problem for the first time, I probably say 95% of the time, I will not see that relationship right away. But I will get there by doing some, yeah, you can say that's kind of just wasted effort, but that's a very well reasoned, very logical process for me to get there. I observe this red shaded area is a relationship between the semicircle and the green shaded area. But the green shaded area is so it's easier than the original red shaded area. But how do I get the green one? I observe it's part of the bigger circle, semicircle that is cut off by this chord. But that immediately gives me the idea because this chord gives me those two radius, give me simultaneous a triangle and a sector. From there, I can see how I can compute the green shaded area. When I put everything together, it turns out this relationship has a more direct meaning, which is you just combine the triangle and the semicircle, then subtracting the green sector. But you don't have to get there in one shot. You can take a few multiple steps. Eventually, you will get it right. And that is a very principled, very disciplined way to solve this problem. Okay? You reason one at a time, not trying to take shortcut. Okay? So we will not do the numerical computation, which is really straightforward. Now we talk about the last problem. Well, this problem is very simple, so I don't think we need too much time. Essentially, this is still the same problem, it's a funky area, but this problem, it's so easy, right? Because everything has been put onto a grid. So this is the bizarre shape of the copy, but really, it's just you want to subtracting everything from the big rectangle area. The rectangle is a full one 8 by 7. So 7 by 8, that's 56. We know that. The only challenge is that how can we get the total area of those just remaining part? But you can clearly see we can just partition them into nice area to compute. The first one is very easy. It's just a triangle, right? This is a 2 by 3 triangle. So that's 2 times 3 divided by 2. That's 3. This portion, you can clearly see you can draw a line here to cut off a triangle right here. This is a 4 by 2 triangle, which is also very straightforward to compute. So you at that part, and the remaining, you can see that you can further draw perpendicular here to put the remaining into a 1 by 4 rectangle, and on this left hand side a tiny another 4 by 1 triangle. So essentially you partition whatever you need to subtract into smaller regions until each region is obvious, clear what it is and how to calculate its area. So essentially, you draw 2 lines here, all at this just kind of turning point, one horizontal, one vertical, to cut this part into 3 parts. 2 are triangles, one a very long, just a narrow rectangle, and of course this remaining part is triangle. So you just add those 4 separate areas together, then subtract that from the total 56, and that's it. So this is a very simple problem. I don't think it's that challenging at all. So that's what we have for today. The big takeaway, perhaps let's take a look at this more difficult problem. The principles will apply to all those kind of funky areas problem. Is that the target is kind of just subtraction, addition, combination of multiple easy to compute areas. The challenge is how to find that particular final combination relationship. You don't have to figure out right away. You can just one at a time simplify it, and then put everything together. You will get that final relationship. Okay? And an important principle is that, say, in this case, you have 2 curves. Why don't you focus on one at a time? Okay? So in this case, we focus on the outer arc first. That give us a semicircle. And that give us what we do this. But we can also focus on this, do the reverse as well. We figure out this part, then see that we subtracting what we call earlier the green shaded area from the semicircle. It's the same thing. You just focus on one difficult curve or segment, whatever, first. Don't try to figure out everything all at once. Do a partial, just solve a problem partially, and then combine that with the other, the rest of the problem. Then you will figure out. Okay, so follow this well-reasoned principle, and you will be able to solve all those problems. But I have to give you a warning. Sometimes a funky area problem can be difficult because it seems that you have no place to start. But trust me, there's always some place to start. And your job is to find that low-hanging fruit, relatively speaking, the easiest part to start. And the rest can be cracked from that point on. Okay? All right. I hope, I think I have to look at the schedule. I think Christmas is coming, so we may not. Let me see. So this is week 13. Yeah. So starting next week, we will have Christmas break. So not until January 9th. So I will find the video from last week and post it into YouTube channel and maybe the Google Classroom. If you are in my Google Classroom, then it's up to you whether you can make it up. All right. All the solutions, of course, on the website. All right. Thank you. Have a great winter break. Bye now. By the way, did everybody watch the World Cup today? I hope you did. What a wonderful, wonderful match.